Electrical system modeling. By the end of this section, you should be able to create transfer functions for an input and output of voltages or currents in LRC circuits, inductors, resistors, capacitors circuits. And you should be comfortable using current loops, voltage drops, and voltage dividers to derive these transfer functions. As we get to see more complicated circuits, you should be comfortable to use impedances in the assisting of deriving these transfer functions. You should be comfortable combining impedances in series and parallel. You should understand how an ideal op-amp works when it's integrated into an LRC circuit and how to derive transfer functions in circuits that feature op-amps. And we'll be continuing to use Mathematica to work through algebraic problems to create our transfer functions. And we're going to see that in these circuits, we often are going to have even more equations than we had in the mechanical systems we previously looked at. What do we do when we start modeling these electrical systems? Well, the end goal is going to be really the same as when we were doing the mechanical systems. We are trying to create a mathematical expression that is describing the dynamics of the system. But in mechanical systems, the states we were tracking or the properties we were tracking were position, velocity, and force. In the electrical systems, the properties and the states we're tracking are voltages and currents. And we want to keep this in mind when we're making our transfer function, that we want to make sure our final transfer function on the right-hand side has no dependent variables, no voltages, no currents. The only thing that should be on the right-hand side are parameters, these constants, and S terms. Here, using a mathematical expression broadly, we will be working with transfer functions as the methodology for making our model when we are working in electrical systems, but you could use a state space model as well, which we'll get to later in this unit. Now, the approach I'm going to go through in modeling our electrical systems is different than what we did for the mechanical systems. In the mechanical systems, we went through a free body diagram. We used the free body diagram to create an equation of motion in the time domain that had a position term, a velocity term, and acceleration terms typically. And then we did a Laplace transform to get it from the time domain into the frequency domain. We're still interested in making transfer functions in the electrical systems, but the procedure I'm going to be presenting and using is going to be completely in the frequency domain from the start. Now, the upside here is we can a little bit more quickly generate our equations that we're then going to use to solve and ultimately create our transfer functions. The downside is we're doing everything in the frequency domain, so we're not going to be starting nor returning to the time domain. So if we want to use a different modeling approach that's in the time domain, like a state space model, then the procedures I'm going to be presenting might not be quite as useful if that is your end goal. But for making a transfer function in the frequency domain, it's going to be a little bit easier. What we want to be keeping in mind as we're generating equations is we are going to need as many unique equations as we have outputs in order to derive our transfer functions. With these electrical systems, there's a great potential that we can create many more equations than we have outputs. However, that doesn't mean that we're generating linearly independent equations as we keep adding more and more. We're going to see that even in fairly simple electrical circuits, there's a lot of different ways we can generate the required equations, depending on if we are using a loop equation or if we're going to be using voltage drops between elements, or if we're using a voltage divider. We just want to make sure that we are generating linearly independent equations and know when we have enough to solve for our transfer function. Again, there is not necessarily one unique path to take to generate the equations that we're going to need. Now, how are we going to work in the frequency domain to create these equations? Well, we're going to start by looking at just these LRC circuits with these three element types: resistors, capacitors, inductors. And what we're going to be looking at is what is the voltage drop as we go across each of these elements. So we'll start with the resistor, and this will go back to what we looked at in the first topic where we were reviewing our electrical components. So a resistor is going to follow Ohm's law, that the voltage across it is equal to the current across it times its resistance. And here I'm going to be using lowercase e to denote voltage or potential difference, but sometimes we will also use V to denote that. We try to avoid using V so that we do not confuse it with velocity, which is also lowercase v, so I will usually be using E and V interchangeably in these electrical circuits. So we can calculate the voltage drop by the current times the resistance. So again, we're trying to work right from the frequency domain with this procedure. So what I can do is take the Laplace transform of both sides. So little e of t will go to big E of s, little I of t goes to big I of s, and then r is a constant, so it just remains r. So the voltage drop in the frequency domain after the Laplace transform, E is I times r. Then we can look at capacitors. What's the voltage drop across a capacitor? Well, we know that there's a relationship between the derivative of the voltage across the capacitor, the time derivative, and the current across the capacitor. So the capacitance times the time derivative of the voltage across it was equal to the current. So what I can do is take this, I can do a Laplace transform. The C is going to be unaffected. The derivative of little e of t becomes s times big E of s. A derivative is just multiplying by s when we're in the Laplace domain. And then little I goes to big I. And I can rearrange this because I want everything in terms of voltage drops. So isolating the E of s term, I can say that 1 over C times S times I is equal to the voltage drop across a capacitor. And finally, the inductor. We know from before that the voltage drop across an inductor is equal to the time derivative of the current across the inductor times the inductance L. So once again, I can take the Laplace transform of both sides. So I'll get that big E of s equals Ls times I. Once again, the derivative in time, the time derivative of I is going to be s times big I here. So these three equations are what we're going to be using when we are calculating the voltage drop across each type of element that we're going to see in these LRC circuits. And notice the difference here in the placement of the S, at least in this form, that there's no just S term for a resistor. We divide by S for a capacitor, and we're multiplying by S for an inductor. And the different placement of the S, either not at all the denominator or the numerator, is what is going to cause us to have these higher order systems. And these will be analogous to having a spring or a damper or a mass in our system. And we're going to see that come into play as we are creating our transfer functions. Now, how do we use these elements to actually generate equations? We're going to be starting by looking at Kirchhoff's laws as a way of generating equations that incorporate these different elements that we're going to be able to put together to get our desired transfer function. So we'll start with the Kirchhoff Voltage Law, or KVL. And this is going to work on any closed loop in a circuit. So we'll talk about it kind of in the abstract and then bring it down a little bit. So if I go in a closed loop around a circuit, then what I'm going to find is that if I add up all of the voltage drops and voltage increases along that loop, and I get back to my starting point, that the sum of all of those voltage gains and losses has to add up to 0. And really, this is coming from the conservation of energy. If I'm getting back to my start point, I cannot have a net gain or loss of energy in my system. It can be transferred into other forms, but I can't gain it or lose it. So again, we're going to be starting and ending at the same node when we are going through the KVL, adding up all of these voltages. And what we're going to see along this loop as we go by is we are going to be able to add and subtract voltages from voltage sources as appropriate, depending on, are we going from its negative terminal to its positive terminal, which way we are saying the current in the circuit is going, and we'll see this in a little bit when we look at some examples. And then as long as we're going with the direction of current across an element, we are going to see a voltage drop across that resistor, that inductor, or the capacitor. Now, if on our path we are going against the direction of current, we would actually add that voltage into the equation as we go through our closed loop. And we're going to see that in more complicated circuits, we can actually have multiple current loops, as we'll see when we get into the examples. And it's going to get more complicated with the multiple loops because we have to consider the total current that goes through each element that we pass over. Then the other Kirchhoff law that we're going to be using is Kirchhoff's current law, again to generate equations that we are going to manipulate to get the transfer functions that we would like. So here, instead of going in a loop from one node to other nodes and then back, for the KCL, the Kirchhoff Current Law, we are looking at what is happening at one node. So if we see a node like this, we have, in this case, current coming into the node, like in I1, I2, I3, and then current leaving the node in I4 and I5. So what the Kirchhoff Current Law is saying is that if we add up all the currents coming in, and that has to equal all of the currents going out, or the net current has to be 0 into any node. And like with KVL, this is coming from the conservation of energy. A node is not able to store any energy in it. So everything that comes in has to leave, and no more that can leave than comes in. So when we assign currents in our system, we have to add all of the currents going in will be positive, and then we're going to subtract all the currents that come out of any node that we establish. And we have a couple of other ways of getting some equations that we're going to be using. So we want to remember that in an electrical circuit, the voltage drop between two nodes is the same regardless of the path that we take between them. So voltage is not going to split from node A to node B. Current will split, and that will be important when we get to our more complicated circuits, especially when we integrate op amps a little bit later in this section. So there are some simplifications that we can make when we have multiple elements put together. So right now I'll just talk about resistors specifically, but this will apply when we talk about impedances later, which is going to be a technique for simplifying our circuit to get some desired equations and ultimately get our transfer function. So resistors in series, and eventually any impedance in series, what we can do is to find an equivalent resistance or equivalent impedance is we're going to simply add the resistances together. Now, we actually could have done techniques like this in mechanical systems, but the downside of simplifying multiple springs together or multiple dampers that are linked together in series is that we are going to lose the ability to track the nodes between those springs or between those dampers. So we won't know what their position is as we're analyzing the system. The same is true in these electrical systems. Is if we do simplify a bunch of elements into an equivalent element, we are losing the ability to see what the voltage is or what the current is across the individual elements that we are simplifying. And it might not matter if we're not too concerned about what the voltage or the currents are across those elements, but we are losing some information in that simplification. If we have resistors, or again, any impedance element in parallel, well, the equivalent resistance of that setup is going to be the harmonic average of those elements. Now, here, that is written as 1 over the sum of the reciprocals of the resistances, but again, that's just another way of saying the harmonic average of their resistances. And finally, we're going to be using voltage divider law sometimes in order to get our equations. So here specifically at the bottom we have a ground. That's not always the case. This can be some other voltage here. But in this more simple case, what we can see is that the voltage in this lower section is going to be equal to some ratio of that total voltage from the V in to, in this case, the ground. That's why it's 0 here. And that piece of the voltage between V out and the ground is going to have the ratio of the resistance between here and the ground versus the entire resistance from the input to the ground. So that's how we deal with these different LRC elements in the system. We also are going to have typically some voltage source in the system, and we need to account for that when we are using a Kirchhoff Voltage Law or Kirchhoff Current Law if we were to have a current source, which we'll typically see less often in these electrical systems. So what we need to pay attention to is the direction that the current is traveling and then the polarity of our voltage source. So if our current is traveling from the negative terminal to the positive terminal of a voltage source, we are going to add the voltage from that source, or the electric potential through that source. Now, if we're in a circumstance where the current is traveling from the positive terminal to the negative terminal, then we are going to be subtracting that voltage in our equation. Typically, this would come into play in a KVL equation. So graphically, it might look something like this in a very simple circuit. If I have assigned I going clockwise in this circuit, we would say that we would be adding this voltage on if we were going with a KVL calculation, as we're going to see soon in the examples. Now, this is my preferred way of representing a voltage source, is that it's very clear which is the negative terminal and which is the positive terminal. But in other sort of schematics and layout diagrams, you might see different representations. So these are two other ways that voltage sources, or maybe a constant voltage source like a battery, might be represented, and it has the same polarity as how it's represented up here with the clear negative sign and positive sign. So the short end, when we have a representation like this, is the negative terminal, and the long is the positive terminal. And sometimes there's two stacked on top of each other, where it's the same interpretation. The shorter end is the negative terminal, and then that top longer end is going to be the positive terminal of the voltage source.